let's get down to business now. We just went through some clicking. Our main topic for the day is basically applying Kepler's third law. We already talked about the first and the second, and we're still kind of working on the third law. This is, as I mentioned earlier, this is the version of it that you would use in the solar system. It works perfectly fine. Johannes Kepler figured this one out. And then Sir Isaac Newton, through the law of universal gravitation, which we'll study in a minute, figured out this one. We've talked about that one already. Okay, we just did some extra clicking practice. And just so you know, these instructions here will be printed on the test. All right, these are the ones that we just followed. Here are the questions that we just did. And by the way, the answer, in case you wrote down the questions, for number 1, C. For number 2, depends on how you expressed it. I just wrote in the word perigee. That's fine. And then I hit the send key. Number 2, the distance from Earth to the Sun. You don't need commas because it's 500 light seconds. I don't know, maybe you were thinking about kilometers or something. So now our break is over. We're switched over to the regular clicker session. So now this is going to be in the regular YouTube. And just to let you know, the self-paced polling will work in a similar manner, except you'll be working off the paper, the exam handout. And it's usually the last page of the exam. Now, I went and looked at one of my exams from my physical science class, and it happens to be exam 2 from the spring. And there's the clicker question page. And you see this picture of a polar bear. We were working on thermal physics and stuff. So that'll be the last, something like that. And so in general, here's what the exam will look like. You'll have a cover page like this one. Now this is for a physical science class, not for astronomy. But you'll still have, last name and first name. You'll write in your PID at the top for extra safety. The date will be up there. It'll say, instead of saying exam 1, it'll say exam X. It'll give you the test form, and that's important, actually. It's the biggest letters on there. Because when you bubble in your Scantron, if you don't bubble in test form A, B, C, or D, it won't get graded. And then you'll be SOL. You don't want to do that. All right, and then down at the bottom of the cover page, there might be, on this test, there's something about box cars and specific heats of water and stuff like that. Now, you guys, what I might do is give you a little table of eccentricities on the cover page, and then in the interior of the test, like question 17, I might ask you about something about that table of eccentricities, something like, which we had in lecture on Tuesday. The cover page will look something like that. And it'll be pretty simple for us. Now, the first page of the actual test is for physical science last spring, looked like this. And I want to show you this one in detail because this one shows you the matching. So here's what it will look like. As I mentioned, there's A, B, C, and D are a bunch of formulas. Now, those are not our astronomy formulas. We have different formulas. But those were the ones that we were studying for exam 2 last spring. And then number 1 and number 2 down here are, okay, there's the definition. There's the vocabulary term. Kinetic energy, and that matches up to option D. Gravitational potential energy, that matches up to option A. So you'll have some, your matching will be the formulas that we've studied, not too many, 3 or 4 maybe. And then some, like a concept or a name or a vocabulary term. And that'll be the first few questions on the test. All right, and then toward the end of the test, or the very last page, is the clicking questions. So after all the Scantron questions, if we do have clicking questions, and you've seen this page already, here's a close-up. There are the directions that we just used. Matter of fact, the ones that I put in the Keynote file here, I just cut and paste from this PDF file from last spring. All right, so those are the directions, and a lot of you have used them already. They'll be on the test if we use clicking on Tuesday. And then down below, there's the boxcar question number 1. All right, so that's why I have that diagram on the cover page. And then thermal energy calculation up at the North Pole or something. So there's a picture of a polar bear. Now you guys will have questions about stars and ellipses and things like that. And when you're doing those, remember. After each answer, hit the SEND key, send. All right? Now, let me pause. Actually, I'll ask for questions about the exam after we finish with the binary star systems discussions. All right, so let's go and talk a little bit more about section 3.3, Sir Isaac Newton and the law of universal gravitation. I love this paragraph, this part of the paragraph, so I took the whole slice of it. Once Newton boldly hypothesized that there was a universal attraction among all bodies everywhere in space, and that was not a common notion. I've mentioned that before. He's the one that said, well, I think the heavens, the celestial sphere, operates under the same physics as the terrestrial sphere and everything on Earth. And so he was the one that said, let's put them both together. Let's put it all together. All right? And once he had done that, he had to determine the exact nature of the attraction. The precise mathematical description of that gravitational force had to dictate that the planets move as Kepler had described them to move, as expressed in Kepler's 3 laws. I cannot overemphasize that. As a model of scientific exploration and development, what you propose has to rhyme. It has to fit. It has to be consistent with the legitimate observations of people before you. In this case, Kepler. Kepler bagged those laws. He spotted those laws. And what Sir Isaac Newton was doing was figuring out a force law that had to imply mathematically all 3 of Kepler's laws. All right? It also, that gravitational force had to predict the correct behavior of falling bodies. Kepler's thinking about planets, right, around the sun. And Galileo, he was all about, he was about a lot of stuff, but one of the things that he figured out exactly was free fall. And you may think to yourself, Dr. B, free fall, that's pretty easy. Just stuff falls straight down and, or a cannonball or a baseball flies to the outfield. We know how to calculate that. But in the day of Galileo, that was new technology. Matter of fact, all this stuff, Einstein once said, here's a famous quote from Einstein: if we knew what we were doing, it would not be called research. And that's Einstein. Like the smartest, second smartest guy that ever lived. Second or third smartest guy that ever lived. And he was saying, most of the time when we're doing this, we don't know what we're doing. We're trying stuff. We're thinking about it. All right, so Sir Isaac Newton, the gravitational force had to predict the correct behavior of falling bodies on Earth as observed by Galileo. How must the force of gravity depend on distance in order for these conditions, i.e., has to match up with Kepler's 3 laws, has to match up with Galileo's free fall theory, right? How does the force depend on distance in order for these conditions to be met? Well, the way that Sir Isaac Newton figured out, and I read his book, where he wrote all this stuff down for the first time. And basically, if you read his book carefully, you'll see that he's thinking about the moon. And he's thinking about, basically what he's doing is, what if I could drop the moon straight down in free fall? What kind of force, what kind of acceleration would be needed? Now, he knew that the moon was on pretty close to a circular orbit, a little bit of eccentricity. But he said, let me drop the moon. So that's why I made this image here. I'm writing a chapter on gravitation for my other textbook. So yeah, his whole thing was, and this is a lovely picture of his synthesis. Everybody know the famous story, Sir Isaac Newton. The apple fell off the apple tree and conked it right on his noggin, and he developed the law of universal gravitation, right? But this is what he was actually thinking about. He wasn't thinking about dropping apples. He was thinking about dropping the moon. And that is a terrestrial type drop situation, but applied to the moon. And it worked. This is the formula that he developed. And this is in your textbook. We've talked about it already. There's the force. The force is equal to a quotient, G times M1 times M2 divided by R squared. Now, I've got a picture here of the Earth and the moon. And they're kind of out of proportion to fit on the screen for distance. But so draw a line between the Earth, the center of the Earth, and the center of the moon. So that's my yellow dashed line. All right, now that's the distance. So Sir Isaac Newton said, it depends on the distance, and specifically the distance from the center of the Earth to the center of the moon, or whatever gravitating object you're studying. All right, matter of fact, let me change this formula here to the mass of the Earth and the mass of L, Luna, the lunar mass. I couldn't find a symbol for the moon, so I just, used the capital L here to represent lunar mass. All right, so the distance dependence is R squared. So you measure the distance, and then actually you square it. You put it in the denominator of a quotient. Now up in the numerator, so go ahead and make a note of that, the mass of the Earth and the mass of the moon, and multiply them together. And then the conversion factor to take a quotient of mass squared, so this is kilograms squared, two masses multiplied together, divided by meters squared. Right? Now that's not a force unit, that's not anything. So capital G is his conversion factor. It's known as the gravitational constant or Newton's constant. And we mentioned it last time. And so he introduced that in there so that it would, like in the British system, did you know that the British system, the unit of force is pound? Pound is not a unit of mass. It's a unit of force. You can take physical science, 1121, if you want to get deeper into that. But anyways, so here's his formula, and he said, and he worked it all out. It all works out perfectly. You get a force on the moon from the Earth, and then you get another arrow acting on the Earth towards the moon. Did you know that the Earth is falling toward the moon? Yeah. It's just that the Earth is so much more massive, we don't really notice it. But yeah, theoretically, they're orbiting each other. They're orbiting the center of mass of the two objects, which is pretty close to the center of the Earth because Earth is so much more massive. But yeah, this is the equal but opposite reaction. You've heard that, Sir Isaac Newton's third law of motion. For every action, there's an equal and opposite reaction. Yeah, that's what we're talking about here. Those two forces are equal in size, but opposite in direction. And it just so happens that once he boldly hypothesized this force law here, everything else fell into place. All right? And here's another quote from chapter 3:3. I really like that chapter. With such a force and the laws of motion, his three laws of motion for any object, like law of action and reaction, for instance, that's his third law. Newton was able to show mathematically, using trig and calculus out the wazoo, that the only orbits permitted were exactly those described by Kepler's laws. All right? So the law of elliptical orbits, all right? The sun at one focus. That's Kepler's first law. Ching! Newton figured out it's the only way that you can have an orbit. The equal areas law. Cha-ching! Newton figured that one out too. And that is rough. That's a rough one to figure out. But Newton was pretty smart. Did you know that he invented calculus? I mean, Newton was like this amazing guy. He invented calculus, universal gravitation. Amazing. And of course, the third law, which we've talked about already, and which we're going to be talking about today. And the textbook authors make this final note that his reformulation of Kepler's third law, in other words, this one down here with all the constants in there, capital G, the mass of the two stars, M1 and M2, and then the semi-major axis, quantity to the third power. It's one of the most powerful concepts in astronomy, as I've mentioned before, because it allows us to figure out masses, of black holes at the center of the galaxy. By the way, I talked to the chief of the observatory, and they're hoping to observe Saturn next Thursday night. The weather's good. So for those of you that are thinking about extra credit, and they'll also be looking at Albireo, which is a star in Cygnus. And so when you're looking at Cygnus, don't forget there's a black hole in the constellation Cygnus, Cygnus X1, a little bit further down the neck than Albireo. So you have plenty of stuff. They'll probably try to take a look at the Andromeda galaxy in the big telescope. So they got a good plan. Hopefully the weather will cooperate. Now we're going to dip. Whoops, I went wrong direction here. We're going to dip back into 3.3 next week when we talk about the outer planets. I want to go through one more thing about that. But for now, that's good enough in Chapter 3. Now I want to dip forward into section 19.2, and which is about finding the distance to stars using what we call the parallax method. And we can't use this for really, really distant stars, but we now have thousands and thousands of stars with really accurately pointing telescopes up in orbit that are, there's the Hipparcos spacecraft, which is now retired. I think it's still up there, but it's run out of fuel and stuff. And then they have another one called Gaia that's up there now, and all it does is measure parallax angles. And parallax, all it is doing a little bit of trig with right triangles. It's nothing fancy. And everybody knows that a squared plus b squared equals c squared on a right triangle. I think everybody's seen that before. And with right triangles, it's pretty nice because if you can measure one acute angle and then one side, so either the hypotenuse or one of the two perpendicular sides, so either A or B, or maybe C, the hypotenuse, then you can get the sides of all the other two sides of the right triangle. Now you got to use trig formulas. Now we're not supposed to be doing trig in here other than Pythagorean theorem, all right? But guys have worked out raise your hand if you've had trig in high school, or it's a lot of you. It's sines and cosines and tangents. It's a pain in the neck. We're not going to go into that. But for those of you that haven't had trig, do not sweat it, because we actually have one trig formula that's really, really easy to use. It's the parallax formula that we'll get to in a minute. By the way, here's a mental IQ test question for you. What do you call a pot of water boiling on top of Mount Everest? Pot of water, boiling on top of Mount Everest. You give up? Hypotenuse. Hypotenuse. Okay, what did the acorn say when he grew up? Geometry. Geometry. Those are my only two math jokes that I remember. It's pretty corny, but anyway. So hypotenuse, trig. Yeah, so we're going to do a little bit of Pythagorean theorem. Check it out. Here's what terrestrial surveyors do all the time. They use lasers now, but did you know that listen to me, Sir Isaac Newton, Abraham Lincoln, Mr. Abraham Lincoln, he was a surveyor in his younger days. And he probably had to do all kinds of square roots and hypotenuses and stuff. But theoretically, what a surveyor will do, they'll try to get a baseline, and then they'll try to take their surveyor telescope there and measure the tilt angle from either side of the baseline to the object, the tree over there that they're trying to, figure the distance to. Or some distant landmark, and surveyors don't measure trees and stuff, but they do measure parcels of land, and they have to do it carefully. And what they do now is use lasers and stuff, so they don't really have to triangulate. But lasers will have replaced this. But in the days of Abe Lincoln, and not too long ago, maybe 20 or 30 years ago, they were doing triangulation, a lot of triangulation. All right. So you figure out the base. So you measure the distance between you measure over there at point A, then you walk off so many yards to point B, measure again, and then use your trig formulas, your trig tables and stuff, and figure out the distance. So if you're a surveyor, you got to know a little trig. Now for us, parallax is a little bit, it's a version of triangulation. But in astronomy, it's for really, really, really small angles. All right. Now, I want to guide you through a little exercise here in the lecture hall. All right. And to show you what parallax actually is. All right. Now, I want you to take your right hand or your left hand and hold your thumb up. Okay. And close one eye. And, I don't know, cover up the American flag. I'm going to cover up the clock in the back, all right? And close one eye, cover it up with your thumb. Okay, hold your arm out straight. Okay, good. Hold it out straight. And then cover it up with your thumb. And then open that closed eye and close the other one. And what you'll notice is that it'll shift left or right. It's covered with one eye, but then it seems to shift. All right? Anybody notice that? Raise your hand if you can see that. It's kind of a shift. Okay, that's the parallax effect. And the reason for that is that there's a distance, a few centimeters from one eyeball to the other. Okay? For most humans. All right? And that is how we figure out our depth perception. And that is actually mentioned in 19.2. And so this parallax effect, the fact that it doesn't move. I'm covering up the clock in the back there with my thumb. The clock doesn't move. It just appears to move. What moves is my telescope. I'm using one telescope on one side of my head and one telescope on the other side of it. And that's the motion. So so make a note, parallax is apparent motion. It's not true motion. Although we can use it to measure true motion. If we make a series of measurements over the years, then we'll see, the parallax might change a little bit. All right? From 2017 to 2027, and then you'll know, okay, that star's actually moving. It might not be moving, it might not appear to move very fast, but it would be moving. All right, now, here's the diagram, figure 3, from your textbook, that I want to talk about. And this is a fairly simplified view, And here's the target out here. And just so you can have decent looking triangles here, do you see the right triangles in there? They're in there. You know, here's the baseline from B to A. And so B over here is like June, and A over here is like December. All right? And so the target is out here. Now that's not a star. A star's not that close. The angle, the parallax angle is this one right here, half of the, so you got this triangle from B out to your target, and then back to A, and then B to A is a straight line through the sun, 2 astronomical units. That's your baseline. So make a note, BA on this diagram, figure 3, is the baseline. Okay, 2 astronomical units, pretty nice. And so if we can measure an angle P, then we can measure the distance. Now this might be, a planet. This is far enough to be a planet. And here's Earth's orbit here, all right, around the sun. So, I don't know, that might be somewhere out past Jupiter somewhere. Triangulating out that way. And of course, now that we have radar and lasers and stuff, we can distance things in, just timing the laser pulse out and back. Like they do on the Channel 9 Eyewitness News weather report, Doppler 9 radar and all that stuff. But triangulation works just as good. And in astronomy, that's what we have to use. All right, so you aim, basically, here's the philosophy. You aim the telescope differently in June and December. To see the same object, you got to tilt it a little bit to the right. You can think about it this way. To cover up the same object, you actually have to move your arm, so, a few degrees left or right. Close one eye, open up the other eye. You got to, change your where your arm is. Okay. So now, as I said, this target here is a little bit unrealistic for astronomical parallax because this is for something inside the solar system, for which we have other methods of measuring. But for stars that are nearby, like Alpha Centauri and 51 Cygni and all the others, we have very, very tiny parallax angles. And so the trig formula for it is pretty basic. Now, here's a comment from section 19.2. As Earth travels from one side of its orbit to another, it graciously provides us with a baseline of 2 astronomical units, approximately 300 million kilometers. Now, if we can then sight in on a star and get a parallax angle, we can do the trig. All right? Now, for very, very, raise your hand if you've had calculus in here. All right. Limits. One of the favorite things about calculus. In the limit of very, very small angles, this is a trig formula. The distance is equal to 1 divided by that parallax angle. All right? And then the distance, we would say, is measured in units called parsecs. All right? Now, let me go back to the previous slide. All right? This is the parallax angle here, P. Okay? So you do this triangle, and then you do a perpendicular bisector from your target over to the sun. All right? So this dashed line, it goes right through the middle of the main triangle. All right? So that's what forms the right triangles. So you're looking at 2 right triangles here, and the common side is that dashed line down to the sun. Okay? And the slivery angle up there, P, that's the parallax angle. Now for something in the solar system, that's going to be a few degrees. Easy as walking through the park. But now for something out to the distant stars, it's very slivery. And all that, you don't have to go to the trig tables, you just use this formula. You just take the parallax angle in arc seconds. All right? And so, for instance, if your parallax angle P is 0.10 seconds of arc, then you just go 1 over that. Take your calculators out because you're going to do a calculation here in a second. What's 1 over 0.10? Take out your calculator or get ready to do it longhand because you're going to have to do a clicker question in a second, calculating a distance. Okay, who's calculated? What's 1 divided by 0.1? It's equal to 10. So for this star, if I measure it December and June, and I get a 0.1 difference in the aiming angles, just a slight smidgen of a arc second, then that tells me, do the trig and everything. The distance is 10 parsecs. So, Dr. B, that's very nice, but what is a parsec? That's an abbreviation for parallax seconds, based on, our terrestrial baseline to astronomical units. So how far away would a star have to be? Parallax of 1 full arc second. It would be approximately 206,265 astronomical units. And that's about 3.26 light years. So 1 parsec, using this trig formula up here, and that is a trig formula, d equals 1 over p for very, very small angles. 1 parsec is 3.26 light years. And some astronomers, they just work in light years. Other guys work in parsecs. Megaparsecs for galaxies, or mega light years for galaxies. And most we don't usually measure stars, distances to stars in astronomical units. Although you could. It's a big number. So usually what we do is light years or parsecs. All right. Now, questions about this before we continue? Because I'm going to give you a clicker question here in a second. And this one's going to be a numeric answer. Question? Yes, in front.
How did you get 1 divided by 0.1?
It's this formula. You take the parallax angle of 0.1, and then you just, go 1 divided by that. All right? So the reciprocal, so think of it as a reciprocal. The reciprocal of 0.1 is a tenth. The reciprocal of 1/10 is 10 over 1. Okay? Now you're going to have a trickier angle here, but a real angle in just a second. Question up here.
So astronomical parallax is just to measure distance from Earth?
Parallax, yes. Parallax is used for us here on our 2 astronomical unit baseline of Earth's orbit. But a lot of astronomers would like to park a good telescope up on Mars or one of the other planets, and then they'd have a bigger baseline. And yeah, so Earthbound observers in space, the spacecraft that we have up in space, the Gaia and the Hipparcos, it's basically the 2 astronomical unit baseline. But, even going out to the moon would be an improvement. Putting a good telescope up on the moon. It's mostly for stars, yeah. Stars and nebula. And we can't use parallax. Even our best telescopes can't get too far away. We can measure thousands of light years out, but like a million light years, we can't get that far out with parallax. We have other methods for doing that, and I'll be going through that later in the semester. Question?
Will we always be given the parallax angle?
Yes, you'll always be giving just like this question that we're about to do. Okay. Another question. Although I'm not saying it's going to be on the test, but if it were on the test, Yes, you'd have to be given the angle. Question in the back. You good? All right. Anybody else? All right. Question number 4 for today. Series A and B. All right. 0.38 arc seconds. What is the distance? So if you don't have a calculator, you're going to have to do this on pencil and paper. 1.000, and then divisor 0.38. So you do it either 5th grade longhand, long division, or use your calculator. All right, and turn on your calculator, if it's still on, hit the refresh key. Okay, and you'll now have the number 1 in there, and you can change it up or down to 0. And the decimal point, I believe, is up there somewhere. There's a where are my specs? Here they are. There's a decimal point. We getting answers? Go ahead and pop the histogram. There's a negative sign. Oh, you know what? You know what's interesting on this clicker? The decimal only comes with 0 point. So if you want a decimal, like 4.6, let me get a 4. Okay, so if your answer is 4.6, and I'm not saying that it is, but you type in the 4 and then go to the right, and then go and find your decimal. Yeah, then the decimal is right below 0. 4 point. So you can select that and then go to the right again, and then, all right. I just sent that. But if you don't like it, you can just go and delete. Change it to 4. Dude. 4.2. Or anything else you want. Right, and you'll get a check mark. And oh, by the way, there's a little 1, 2, 3 kind of on the right in the middle of the display screen. And that'll indicate that it's only looking for numbers and decimal points. And actually, there's a minus sign in there too. So, okay, how many? Okay, 30 seconds. We're doing good here. $20 seconds. That's good. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Zero. Go ahead and show this. And it looks like a lot of you voted for 2.6. A few of you voted for 2.63. See if you can scroll down. So look at this guy that typed in 64. I don't know how you get. I'm not making fun of that. What I'm telling you is I would study that and see if that guy has a, like a typo. No, don't laugh. I don't laugh at your data when I'm grading your tests. Usually. Unless you... See, but this will record... Whoa. That's a big one. That's 10 to the 18 parsecs is a long way away. Anyways, you can see the most popular ones. And as I was saying, I don't laugh at your data unless you type in something like a Chuck Norris joke or something like that, which, if you're totally stumped. But don't do that on the test. Try to give it a good shot, because I'll give you partial credit, because I look at every single answer, all 300 of yous. Some of them will be right on the money. You get the points automatically. But if you have like 2.63, I might give that student partial credit because they didn't round off the way I asked them to. All right? But 2.63 might be kosher. If I had asked for 2 decimal points, that might be a good answer. I forget what the second decimal point would be. But then 64, I'd say, no. 0, no. 2.7. 2.7 is? Bad round off. So that's somebody that did it, 2 people did it on paper, and, they're a little rusty with their 6th grade long division stuff, but I might give them 1 point partial credit for something like that. Okay? So I'll try it. This is one of the reasons I like using clickers on exams, specifically because I can look at your stuff and give you partial credit if you're close, which is nice. All right, we want to do that. All right, go ahead back to the regular display. All right. So here's your formula. There's your answer. Go ahead and write it down, 2.6. And if you multiply that number by 3.3, you get 8.6. So in light years, it's 8.6. All right. And so we have just calculated that is the parallax for Sirius. What you just did, 125 years ago would have been, you'd have been a rocket scientist to do that. And you guys just did it, so it's good. You guys are doing good. And most of you did get that one right. Can you go ahead and score that one? And score. Go ahead and look at all the different answers, and you can select them correct or not. All right? Just be compassionate. That's good. That's good. Somebody had a 26. That's good. We're grading your work up here. So somebody had a 26. You know what that is? A 26 instead of 2.6? That's somebody that didn't bring their microscope, because you can't see that decimal point. It's just... Anyways, go through that. And let's continue with the upshot. And here we go. Getting the parallax angle and having a baseline here, 2 astronomical units for our orbit around the sun, allows you to figure the actual number of light seconds or light days for something like Sagittarius A star and its faithful companion star S2. That's how we get it. So we get the semi-major axis here in terms of arc seconds. And then remember last time we converted that, or I gave you the conversion of that into light, I think it was light days. What was it, 46 light days? Look back in your notes. Semi-major axis for S2. I think it was light days. You see it? 5.5 light days. Okay. All right, so that's how you get that. 5.5 light days. Now you can do Kepler's third law and get the mass. So this whole thing about Kepler's law, you have no idea And here's the punctuation for the entire semester. This gets us right down into the middle of the semester of almost everything that we talk about. If you know the mass of a star, you know its DNA. You know how big it's going to be when it's born, how long it lives. You know what color it's going to be. You know everything. Like for humans, you look at the DNA of a little baby before it's born. I don't know how you could figure it out, but you could figure out supposedly the fingerprints and the eye color for sure, and the hair color and the skin color, all that stuff. How tall they're going to be when they're your guys' age, roughly. All that stuff's in the DNA. The DNA for a star is one number, the mass. Now, let's spend a few minutes talking about exam X. My wonderful students, this is a diagram of Sirius A being orbited by Sirius B. Be ready for my standard exam strategy. One or two brain burners to really separate the top students from the tippity-top students. Plenty of basics, just going, trotting you through the basics. Okay, do you know what a parsec is? Okay, do you know what a parallax angle is? Do you know what a, all the different things that we've talked about. So do your normal amount of studying, and it should be tough to flunk. Do as much studying as you possibly can, and it should be tough to ace. But, not impossible, just tough to ace. In other words, tough to get 100%. You might be able to get 95% or even 96%, but to get all the way up to 100%, if you're leaving now, you're going to miss out on some tips for the test. I'll announce over the weekend if there will be clicker questions, all right? And it'll be in discussions or something, so keep an eye on that. And for those of you that stayed, I'll just tell you this. You might see this diagram on the test. And just think of all the questions I could ask you about that one diagram. Especially if I give you a few numbers. Its semi-major axis and its eccentricity. Here's another thing I want to go over with you, and it's something I talked about with a student in office hours yesterday. She was saying, Dr. B, what's a good strategy? What's a good strategy for really knowing those equations and stuff? Here's one thing that you can do with your study partner, if you have one. Try to find a study partner. And I don't know how it's going to work on that Snapchat study group. We got about 1,000 study partners, but for every equation in your notes, try to write down a description of it in two different ways. How did Dr. B describe this equation in class? And two, how would Dr. B or an astronomer use this equation and why? And if you can take every equation and just write a little simple sentence about, or two simple sentences like I just mentioned, that's going to really help you savvy the equations that you'll find. And on the test, if you have to make a calculation with them, it'll make your calculation go even faster because you already kind of have the strategy for that equation. You won't just be seeing, because here, look, unfortunately, in our textbook, they use the letter P to stand for orbital period, and they also use the letter P for parallax angle. I hate to say it, but that can be confusing, unless you do what I said about those 2 sentences for each equation. Then you won't be tripped up. All right? Now you're dismissed. I'll see you guys next Tuesday, and I'll see you in discussions. Come on up to the front if you have a question. Where's my cursor? Here we go.